The next challenge that we want to discuss is dataset size, and we're going to provide some solutions to combat this important challenge. Small datasets are a serious problem for deep learning models. When the dataset is small, it's easier to overfit to the training examples, which means instead of learning discriminative patterns, the model memorizes the training data. And when an unseen example is presented to the model cannot classify it correctly because it hasn't learned anything useful. Now, there are various solutions to combat overfitting. Pre-training is one of them. Data augmentation is another one. Dropout, entropy regularization, and so on. Here, we're only going to talk about pre-training and a recent work we did on data augmentation. So one popular method to combat overfitting is pre-training. Instead of initializing weights from random values, which is usually done when we use deep learning, we first train the model on a large data set. And once the training is complete, we discard the classifier and use the feature extraction layers from previous training and just initialize the weights for the classifier from random values. Now, we could use the pre-trained weights as frozen feature extraction layers and only train the classifier, right? We could use the pre-trained weights as the feature extraction layers, which means that we only train the classifier, or we could fine-tune the entire model end to end. Usually, in papers, people try both versions and see which one works better. Usually, the fine-tune works better, but probably if you have very small data sets, you're better off freezing the pre-trained weights and only fine-tuning the classifier. I recommend trying both and seeing which one works better. Now, using this technique, this paper was able to reach human-level performance on OCT image classification task. And the paper was published in 2018. Now, I need to, it needs to be mentioned that pre-training from natural images, this is something that this paper did, and this is something that is very common to do. But it's not the result, and whether it's helpful or not, it's inconclusive. Sometimes it helps, and sometimes it doesn't help. As a rule of thumb, the closer the pre-training data set is closer to the downstream task data set, the closer they are, the better the result would be. But sometimes pre-training from ImageNet also works. Still, it's something to try and see. Right, so the next common approach for dealing with small data sets is data augmentation. Here, I'm going to talk about synthetic data augmentation, which is a bit different from what's normally done. Conventionally, data augmentation is done by applying transformations such as rotation, translation, color jitter, and so on to the image. While this type of data augmentation can be very helpful, there's still a lot of correlation between the original image and its transformed version. This means that the added examples are not independent. And as you remember, deep learning works very well when the examples are IID, where the first I stands for independent examples. In a paper that we recently published, we took an alternative approach. We trained a generative model that is able to generate diverse 3D lung CT and use the generated CT volumes as additional training data. Just a word of caution, one needs to be careful when of possible covariate shift between the generated examples and the downstream and data from the downstream task. In our case, this didn't create a problem because we were dealing with CT, and you don't usually have a lot of covariate shift between CT data sets. Now, for this purpose, we use generative adversarial networks to generate 2D images and took advantage of bidirectional LSTM to learn correlation between subsequent slices. This allowed us to generate coherent and realistic looking 3D volumes. This generative model was trained on 1000 CT scans from LIDC and NLST datasets. Here are some examples of the generated samples. So in the top row, you see slices from generated samples from different 3D views, and in the bottom you see real images of the corresponding slice locations. So these, because it's 3D, we've taken these slices from the same location of the 3D volume. Now, as you see, the generated images are very realistic, and actually very high in resolution. They are 256 by 256. So the question is, can training on synthetic data help generalization? That's the question. That's why we did this project in the first place, right? So we conduct 3 experiments to answer this question. First, we train on real data 1K examples, and we use all the conventional data augmentations with rotations and flips and all that. And this is the result we have, the dark blue. And the bottom, the x-axis here shows performance of the model on different nodule sizes, right? So of course, when the nodule is very big, that's the only time the model is able to pick up the nodule, and it roughly fails in other cases. Next, we train on 10,000 synthetic data, which are generated by our generative model, and then apply that on our test set. This is the purple one, and you see that it's not doing very well for very small nodules, but it does significantly better when the nodules get a bit large with 14 radius in size, but they are still better than in all the nodule sizes. They are significantly better, or like they are better than only using the real data. And next we tried training with 10,000 synthetic data and then fine-tuning on the 1,000 real data, and this is what gives us the best performance. Right.